solution, and we're going to talk about the first concentration unit, which is molarity. All right, when we talk about solutions, a solution, remember, is a homogeneous mixture as opposed to a heterogeneous mixture. And we talked about mixtures and homogeneous mixtures early on. The solute is the substance that dissolves. And remember, we talked about the fact that it is in minority. So if you have two liquids that dissolve together or are put together, then dissolve is kind of an odd term to use. If you're making Kool-Aid, it's easier a solid than a liquid. And if the solute is the substance that dissolves, the solvent is the substance that does the dissolving. Okay, so when we look at this, just like the solute was in the minority, the solvent is in the majority. So, how do you determine that or classify that or characterize that? Okay, it's concentration, and concentration is a characteristic property, and it's a ratio of the amount of solute to the amount of solvent. Now, there are a variety of concentration units, but we're going to concentrate on one. But before that, you have a general term. Dilute is a small amount of solute in a large amount of solvent. And concentrated is the opposite, large amount of solute to solvent. Okay? So, in a dilute solution, you don't have that much solute. In a concentrated solution, you have a lot of solute. You know, concentrated orange juice. Okay, so these are qualitative terms. Those don't really tell you how much. But quantitatively, the concentration we're going to use is the amount of solute over the amount of solvent or solution. Now, we're going to stick with solution. Later on in 1212, we will give you a variety of concentration units to deal with. But we're going to deal with molarity, which is moles of solute over liters of solution, which is N, which is the number of moles. Molarity is also known as molar concentration. So if I ask for the molar concentration, I'm asking for the molarity and vice versa. They're interchangeable like mass and weight. All right, so we're going to work a couple problems. Calculate the molarity of a sodium sulfate solution that contains 28 grams in a solution. So remember, molarity is moles per liter. Well, if you look at it, you've got the liters. That's 0.750 liters. We have to put it in liters. So what we need is the moles. So to get the moles of sodium sulfate, we're going to start with our grams, which is 28.56 grams. And we'll need the molecular weight, and that's 142.04314 grams of sodium sulfate for 1 mole of sodium sulfate. Now, you could do that and then divide, or think about it. If you have 6 divided by 2, another way to write that is 6 times 1/2, right? So if I need to divide this by the volume, then I can just put that in there. And if you'll notice, your grams cancel. You're left with moles per liter, which is the molarity. That's 0.2680876 molar. which if you look at the values, we have 3 significant figures. So you get a value of 0.268 molar is the concentration. Okay? Now, you could split it up and do it separately, and if you had stopped right here and just found the moles, you would find that it is 0.2010656 moles, and then you could divide by the volume. Whatever makes you happy. I like to work it in one step. Okay, I'm a little strange that way, but I like it. All right, so then the second one says is we're looking for grams of the salt, which in this case is cerium sulfate, and we're got an amount and a concentration. Now, note, concentration has 2 units. It's moles per liter. So it's actually conversion. So that is not an amount. If we're working problems, it's easiest to start with amounts. So we have 258.2 milliliters of the solution. Now, the molarity is in moles per liter, so we need to convert that to liters. Do you have to do it on paper? No, you can do it in your head. That's fine. So we're now to liters, and we know that this is 0.150 moles per 1 liter. Now, molarity is like density. The number stays with the moles, and the liter is assumed to be 1. So our liters canceled, we're left with moles, but we're asked for grams. So we would need to calculate the molecular weight, which happens to be 332.2472 grams per 1 mole. So we end up with 1.28679 grams. We look at it, we have 4 significant figures. Wait, no we don't. We only have 3 significant figures because this one is 4 significant figures. This one's infinitely, but this one's only 3 significant figures, and this is a lot. So we're 3 significant figures, so we will report as 1.29 grams. Excuse me, of salt are needed here. Okay? Remember, molarity is like density. The number goes with the unit. Okay? Work another problem here using a 1 molar potassium chromate. How many moles are present? Okay. So really the take-home message here is we want moles of potassium chromate. We're going to start with our amount. And our amount is our volume. So I'm going to go ahead and convert it to liters. And remember, molarity is moles per liter. So I need the liters on the bottom. So 1 liter is 1.05. The number always stays with the moles. So we do the math and we get 0.10332 moles. Amazingly, we have 3 significant figures. I really got to change that so we can go back. So 103 moles. Don't assume it's always 3 significant figures because on a test I make sure it's not. Okay? So you can convert these back and forth. It's like the density. You can be asked for the volume. You can be asked for the moles. You can be asked for the grams, which is a variation of the moles. Or you can be given the grams, solve for moles and a volume, and you can come up with a molarity. So in that respect, it's very similar. Now, this particular problem is a little more complicated. We're starting with concentration. We're given a by mass amount, so that's a ratio, so that's some sort of conversion. We have concentrated there, we have a density here, and so we're calculating. So what we want is the number of moles of HBr. And we're given it in a concentrated solution. So I'm going to call this CHBr. And HBr is just regular HBr. So we're going to start with 0.5 liters of concentrated hydrobromic acid. And we know that we don't have a molarity, so we can't use that. So we've got to get to moles. In order to get to moles, we have to have the grams. So we've got to get from milliliters to grams. So wait a minute. I'm going to have to use the density, which is per milliliter. So I'm not using molarity. So let me go back and erase this. I have an eraser. Yay. And we're going to use 500 milliliters of concentrated HBr. So we know that the density, and that's in milliliters. Oops, lost that. So we know that the density is 1.490 grams of concentrated HBr per 1 milliliter of concentrated HBr. So that got rid of our milliliters of concentrated HBr. Now we have grams of HBr. So we know that for 100 grams of concentrated HBr, we only have 48 grams of regular HBr, just the HBr itself. Now we got that from 48% because 4% means over 100. So you could go ahead and convert it to 0.48 but over 1. But it's just easier to use 48 over 100. So now my grams are gone. And now I need the molecular weight. Oh, wait, I'm looking for moles. I have the grams. So, yeah, I still need the molecular weight, which is 80.91194 grams. And I know it goes on the bottom because I've got to get rid of the grams to be left with 1 mole of HBr. Now, we would pick up our calculator, and everything on top is multiplied. Everything on the bottom is divided. And so we get 4.4196197 moles. Now, significant figures, how many do I have? Well, this decimal was there, so that's 3 sig figs. This is 4 sig figs. This is 2 sig figs. This is 2, 4, 6, 7 sig figs. So we have a winner with 2 sig figs. So 4.4 moles of HBr are found in the concentrated hydrobromic. Now, this is a real simple calculation. This particular one is a little more complicated, but we're going to need the simple molarity when we do solution stoichiometry, which is the last step in this chapter. So, take a look over this and be ready to move on.